was just going to talk briefly about some performance test benchmark test suite, benchmarking test suite, performance test suite that I've recently added. So I guess this was a long time coming. MicroPython really hasn't concentrated on performance. I mean, that's kind of not the right thing to say, but we haven't really had good performance measuring tools to see what is improving performance and what's not improving performance. And up until now, most of the things have been, we want to make it use less RAM and be small and fit on a microcontroller, but there comes a point when you want to increase performance and you need a way to measure it well. So that we've been using this Pystone benchmark for a long time just to do basic performance analysis. So Pystone is like, it's just a script that you run until it gives you a score. But that only tests sort of, that doesn't test too much. It doesn't test flows, it doesn't test like real classes and things. So I wanted to make more nuanced tests that could test actual different parts of the system. And so I'll just show you the output of it and then explain it. Let's just do 1000. So there's a bunch of tests here, and it just ran them all and gave the scores. So there's 4 columns of data. The first one is the time taken in microseconds. The next one is the variation in the time. So there was actually 8 averages, 8 runs that were done of each test. It says at the top there, and average is 8. So it ran each test 8 times and averaged them and got the standard deviation, which is that 5.35 in the first line. So that BM chaos took 38.9 milliseconds per run with an average of standard deviation of 5 microseconds. Actually, sorry, that's wrong. That's a percentage standard deviation. So there was a 5% error in that measurement. So the actual standard deviation in microseconds would be for about 2 milliseconds. So 38 milliseconds to run, plus or minus 2 milliseconds. And then the next column, the third column, that 25724.50, that's a score, which is sort of the inverse of the time. So you want low time and you want a high score. So the score is just, it's kind of like the inverse of the time multiplied by some number to make it largish. And then the last column is the percentage standard deviation of the score run over those 8 times. So usually I just look at the score column and then the score standard deviation or error, and I'm like, okay, this is the score it got, and the ones that have really low error, you can be confident that they were pretty good. So the second line there has only a 0.4% error, so you can be pretty confident. And if we if we just run that BM chaos again, you can just run one of them. So this time my score was 26,000, before it was 25,000.7. So there is variation. And if I run it again, it's going to change, because it's a 3% error or so. Now, the point with this test suite was that I wanted to be able to run it on all kinds of targets. So here it's just running on my computer, which obviously is pretty fast, but I want to be able to run it on anything, and I want to be able to compare absolute values across things, as well as compare changes I make to the code and things like that. So these numbers that you specified, I'll just clear. I had 1,000 and 1,000. They're kind of, the first one is the approximate hertz or megahertz of your target. So in this case, it's a gigahertz, I say approximately machine. And the next one is the approximate kilobytes of memory it has. So it has about a megabyte of heap available. And so it will tune each test so that it runs in about 1 second for that target and uses about as much memory as it has. So you can't run the parameters on a small microcontroller because it doesn't have a megabyte of memory and it's not running at a gigahertz. It will take forever. So on those things you do like 100 and 100. So 100 megahertz and 100 kilobyte heap. And if we run that on my computer, you'll see it's very fast because it's it's thinking it's running on a very slow computer, so it's not taking as many iterations in the test. So each test, if we have a look at, just look at this chaos one, ignore what it's doing, but at the bottom, there's a set of parameters here, which is saying given these input parameters, kind of machine, this is the parameters I want to use for the test. So if the machine runs at 100 megahertz and has 50 kilobytes of RAM, these are the parameters here I need to use for the test, and they mean something. So like this, I think it's a 50 by 50 image that it's generating with 100 iterations or something like this. And if I've got more memory, I can do a 400 by 400 image with 200 iterations. Actually, it might be 1,000 iterations here. Maybe a more insightful one, like as a simpler test. High digits is pretty cool. So it just computes the digits of pi. And this tests big num performance, because to compute more, you're using big arithmetic, so you're getting numbers out that are 10 to the 100. To compute subsequent digits of pi, you get larger and larger numbers. So it actually doesn't really test the virtual machine itself, it just tests big integer arithmetic. So it's a good test, because lots of the other tests will improve, say, when the virtual machine improves, but this one might not improve because you didn't improve the big integers. So it's a pretty small thing, and then down the bottom is just, so here's a set of parameters. The first one is, so number of loops and the number of digits of pi to compute. So on a really fast machine, I do the same thing 3 times and I compute 350 digits of pi. But on like an ESP8266, I'll only do it once and I'll only compute 35 digits of pi. So to make a test, you have to actually go through all the different targets and fine-tune the numbers, which is a bit time-consuming, but in the end you get a really powerful test suite to run. It also does actually check the output is correct as well. So it's a self-testing framework. If the output's wrong, then you can't even trust the test. Like if it doesn't compute the right digits of pi, that's not good.
Does it interpolate those numbers, I presume?
Sorry?
Does it interpolate those parameters?
No, not at the moment.
So choose the...
Yeah. So yeah, it's just fixed. Yeah. The parameters are just fixed. But...
Too low?
But I've got a microbit here, which is not very powerful. And if I try and run it on that, so P, because it's running it on a PyBoard script. So it's running it on this microbit here. Yeah, it's working. The micro is actually worse than 50 megahertz, so it will take a bit longer. And you see it's crashing on some memory errors here and there. Just because it doesn't even have... I've said it's 50 megahertz and 25k heap, because that's the lowest it'll go, but this thing's even less powerful than that. But it does manage to run a few of these tests. So this Fancook one got a score of 27, and nQueen's got a score of 116. So if we just try and run it on the computer instead with the same parameters. So Fancook gets about 30,000, so 27 compared to 30,000, so it's about 1,000 times more performant than my computer, than the microbit. And nQueen's, was that the one that worked? Yeah, so that got 116 on the microbit, and on the computer about 167,000, so more than 1,000 times faster. So you can compare these numbers as long as the error is relatively low. So on the microbit, the error is very low because it's very deterministic. Sorry, this one here, 0.03% error in that score. So you can be pretty confident that you got the right number there. So this is running on the ESP8266. Okay, it's trying to connect to the internet and it's outputting some strange stuff. Yeah. Okay. So stop trying to connect to the internet. Yeah, so the H66 is about 50 megahertz and 25 kilobyte heap, so these numbers are tuned for that. You can see the errors are pretty low, these numbers on the right. Percentage error is quite low. So for nQueen's, the microbit was 116, so this is about 4 or 5 times faster than the microbit. For Fancook it was 27, so again about 4 or 5 times faster there. But yeah, you can see there's no matching parameters, means that those things aren't tuned for those parameters at the moment. what I should, okay, those ones should work as well. I'll just stop it there because the other thing I wanted to show, there's lots of stuff to sort of, I mean, I could show you lots of comparisons and things, but what's something quick and easy to do? I'll just run it on here first. There's just one other main feature to show. Yeah. Oh, it's just not flashing. Yeah. So this is just running on a PyBoard with just to get some outputs. Okay, I'll stop it so that we've got enough there, hopefully. Yep, so I've saved the output here, and now I'll just change the frequency. So that thing was running at 216 megahertz, so let's run it, say, 120 megahertz. Okay, and run the test again. It's going to probably take about twice as long, but yeah, the aim is just to show you the script has this other mode where it takes a difference of two outputs. So the idea is that you set up your board or your code or whatever, you run the tests, you save them, you make your changes, you run the tests again, and then you take a diff to see what the performance change was. Okay. So I have two, I have out A and out B. Some of them have, well, they at least have the first 6 or 7 tests. And now if I do, so you run, so I want to diff the scores in out A and out B. And so it shows you, reads in those files, takes a difference, works out also the standard, the error, as in combines correctly the standard deviations, so you can be confident that the difference is real or not. And it shows here there's no difference, so something must have went wrong with changing the frequency there. But yeah, okay, well that's good, I guess. So you want the absolute difference is this column, and that's the difference in the score. But the percentage difference, so that's the difference divided by the actual score. So you can see the percentage difference is less than 1%, and the error is all less than 1%. And in fact, there's no difference within the error. And that's because actually it was running at the same speed in both cases, it must have been. I think I must have to, because when it does a soft reset, it must be. Must be, yeah. Let's run it at 168. So, 100, 100. See. So I'll just do a few, you can see the difference. So yeah, this is useful for testing any new feature to see if it's going to improve or not improve, and also if you're trying to tune your platform to maybe turn on certain optimizations or not, you can see if it's a good thing to turn on or not. Because some platforms behave differently with respect to performance tuning. But run, so difference in scores of A and C. Okay, so C was 168 megahertz and A was 216 megahertz. So going from here to here, the difference is negative, which means the performance has dropped by about pretty much 20%, 21% with a very small error. So if we do 168 out of 216, but how is it done? I think it's 168 minus 216 out of 216. That might give us the 21. Yeah, 22.2%. So the speed is dropped by 22% and the performance of the test is about 21%. So there's almost a linear correlation between frequency of the CPU and the score of the test. So that's I guess this is a verification of the test suite itself, showing that it's pretty sensible. Reduce the speed frequency by 21% or 22%, and you get a decrease in 21% on the actual test performance. The other thing you can do is you can diff the times, so lower is better. So going from 216 to 168 megahertz, we got an increase in time, which is obviously bad. And the increase to 26% or 27% is because the way you do the percentage, it's a 21% loss or a 26% gain in time. It's just maths. Yeah, when you're talking about small percentages, 1% loss is the same as a 1% increase in score versus time. But when you get into large numbers, it doesn't. It doesn't work as well anymore. That it's just maths. Anyway, okay, I'll stop here. But anyway, I thought hopefully you can see the usefulness of this, and maybe you can run it yourself. It's not too hard to run.
That's
Any questions I can answer?
I presume that's in the MicroPython repository?
Yeah, so I'm just in the main repository in the test directory. So run perf bench, and the directory is perf bench where the performance tests are. So there should be more in the future, but at the moment I think it covers like a lot of the test things.
Has it identified anything that you were not sure about?
Yeah, I've been running it now and then on some things, and
surprised you someone?
So there's an option to use like a go-to table in the virtual machine to dispatch opcodes instead of a switch. So you're using a table of go-tos instead of a switch. And I thought the table of go-tos was a lot faster, but on some platforms it's not really much faster at all. Which I guess it just comes down to the way that machine architecture works and how pipelines stuff. So for some ports like the ESP, it might be worth turning that off even because it takes up a bit of code space. So that's one thing. The caching of opcode of lookup. So there's an option to turn on an optimization where when you look something up in a dictionary, it remembers the place it looked it up and it found it. So next time you do the lookup, it looks in the same spot straight away and it might retrieve it, and that is like a fast path for dictionary lookups. And that does improve things a lot, like 20 to 30, maybe 40% speed improvement. And this is not enabled on any of the boards because it means everything has to be in RAM because the bytecode is self-modifying, kind of. So when you run it, when it looks up dictionaries, it changes itself to say next time look up here instead. So, but I've recently been trying to work on a way to do that without it needing so much memory, so we can have that feature on the boards, and it seems to work. So there might be a way to speed up like about 20 or 30% MicroPython across the board on all the microcontrollers, like, for most things. That'll be coming. But all these things can be unlocked now that we have this performance testing, so that we can be confident in what's happening instead of just shooting in the dark.
Had you done any, like now that you've got the benchmarking suite, have you done any tests against like previous releases to see like, oh yeah, it did get better over?
Yeah, no, I haven't really.
Not a lot of point really. But
well, that would be interesting. I mean, there's lots of stuff to do. Code dashboard. There's something very relevant to that. That I'll show you briefly.
Yeah.
Don't get bored, but. So this is the code dashboard. This is the history of MicroPython from the very beginning. It's online. You can go to it.
Mm-hmm.
So all the lines show the size of the ports over time. So like the green line is a Unix port growing over time, and the purple line is like the very minimal one, which is shrinking over time slightly, but it's not growing. But the really fuzzy line is the Pystone performance benchmark run over time.
Okay.
So you can see that there were big jumps going up and then down and then like up a bit at the end, and it's actually more stable now than it used to be. A lot of these jumps here are just changes in the underlying machine, and like the server this thing's been running on has changed over time. The compilers have changed over time. So these big jumps in the code are actually compiler changes and not code changes. And
So that's Python running on the Unix port.
yes, yeah, on a server somewhere, which might have other load on it as well. So it's not. I mean, it's still that it does do averaging, and the noise is actually better off at the end here. But this drop here, this big drop, I think that's when threading was turned on, because that actually does have an info, because you've got to lock and unlock the garbage collector. I think that's what that one was. These increases, the first increase was when that remembering of dictionary lookups was enabled very early on, because that was a feature that was added a while ago. And I think maybe the other one was go-to tables, because on the Unix port that made a big difference. But yeah, you can see threading decreased it, and there were some other things that decreased it, and then a few things that increased it. It's yeah, so it's something to look at. You can go back over time with the new test suite and actually see, because this was just one script, the Pystone thing.
Yeah.
So to run the full performance benchmark would be interesting on a fixed machine that gave you low errors as well. And then you could see maybe what things could be improved to improve performance. But yeah.
Cool.
Also, I guess you could compare it to CPython eventually. I mean, yeah, you can as well. So there's lots of fun things you can do with this. And, but yeah, it's good things there.
Have you documented some notes for us, so we know how to use it?
No, there's not, apart from what I've said now, there's not really any documentation. Like, I mean, it's just, yeah.
It is, yeah.
So, but we can,
YouTube can.
it's not too hard to document. It's just the location of the script and how to run it. Yeah, so it's not, even those commands like that how to diff things, that would be good to document it, yeah, for sure. And then you can try it out yourself. So that's something we can do. Yeah, we'll do that. Okay. Make a note. Document performance. Okay. Anyway, but yeah, so it's, thanks for listening.
That's great. Thanks.